Okay, today's lecture is an extension of the timing that we talked about last time, except we're going to talk about discrete parts. So if you looked at discrete implementations, and I'm not sure what you used in 1901, but you used some various part numbers, right? They might have said CD54HC174 or SN74LBC2 dot, dot, dot. So we'll talk a minute here about what all those things mean. So there's 1, 2, 3, 4, 5, 6 categories here. The first is the manufacturer prefix. So in this case, HD, if we look down the list, belongs to Hitachi. SN is Texas Instruments. And you can see LM is National. Notice some of these names don't seem to match the companies at all. Let's look here. ON says it's MC, but ON was actually used to be Motorola, and a portion of Motorola was sold to ON Semiconductor, but they keep the old names. We can probably find another one here. Here's Siliconics, which used to be owned by somebody else, so their signal is DG instead of Siliconics or something that looks like it would be Siliconics. So the first section is the name of the company. The second section is the operating conditions. So generally it's mostly around temperature. So if it's a 74, it's commercial grade, which means it operates from 0 to 85 degrees C. If it's a 64, it's industrial, so minus 40 to 100. And if it's a 54, it's a military or an aerospace grade, and those operate from minus 55 to 125 degrees C. And the third section is the kind of technology that was used to build this part. And there's three general classes of technology here. One is Schottky, TTL, which is pretty much gone, but still around a little bit on older boards and things like that. The second is all the CMOS technologies. And the third is BiCMOS technologies, which are kind of a combination of the bipolar and the CMOS together. The next section, the gate counts, you rarely see this in most parts, so I'm not even going to talk about it, but it's how many gates are on the part. But it's not used a lot of times, as you'll see here as we talk about the device number. So the device number is a name for the kind of device that it is. So you can see a 7400 here is a quad 2-input NAND gate. And notice that the 7400 by definition is a quad. And so that's why that gate count number isn't used very often. Most of these in their device numbers specify how many are on the part. We can see that 7473 is a dual JK flip-flop with an asynchronous clear. A 7477 is a bistable latch. And then the last one is the kind of package. You see there's a bunch of letters and acronyms there. There's lots more than what's on this short list. We can look at some of those packages here. You can see that there's a 84-pin PLCC up here in the upper left. Plastic leaded chip carrier. The one you're probably most familiar with would be like the 14-pin DIP, which is a dual inline package. If we go just below that, there's a pin grid array, which means it's got a bunch of pins sticking out of it straight down. And below that is the most common one for at least high-density technology, the things in your phone or your laptop and things like that, and those are called ball grid arrays, and they're just a whole series of balls on the bottom of the package, and those get laid right on top of the board. You can see there's all kinds of different kinds here. All right, so if we start looking at one of these data sheets, so this is the SN74 LS74, but the thing to note about this data sheet is that it actually covers a whole bunch of different parts. You can see up there in the right-hand corner here, SN54, 74, 54LS, 74LS, 54S, 74S. So it covers a bunch of different parts. It makes the spec a little bit messy because you have to keep track of which part you're looking at. And then just to remind you, the SN is TI, the 74 is commercial, the LS is low power Schottky, and the 74 is a D flip-flop. So I think we're going to look at that data sheet real quick here. All right, this is the SN5474, 7474 on data sheet. So again, there's generally going to be some sort of a picture of what the part looks like. Notice this comes in different types of packages. So it comes in the dips, and here's a quad package. It's got the function table for something like this. It's got a symbol that you might see in a schematic somewhere. And then it's got this little logic diagram, and we can look at this and see, all right, this is pretty similar to what we drew, but not exactly the same thing. And these logic diagrams are usually simplified versions. All right. Then there's some input-output circuitry that's going in here, and we're not going to get too much in discussion about this, other than to realize that these bipolar or these TTL parts require input current. Unlike the CMOS we've been talking about that doesn't have any input current, these bipolar devices do have input current. Here's an actual schematic. So if you ever wanted to go figure out how one of these things work, they provide the actual schematic in some of these older parts. So you could follow that through if you wanted to at some point. And then there's just specs after specs after specs after specs after specs. Here's a bunch of packaging information. Right, more packaging. You can see this thing comes in a gajillion different types of packages, and then all the end notes that come with this. All right, so that's the. All right, here's actually how it's shipped. You can buy it on a long reel, which means there's just thousands and thousands and thousands of these stuck on a reel. You can buy it on a tape. So this is like an audio or a video tape that has parts. Okay, so now if we look more closely at some of the specs, I pulled some out here to put them onto the slides. The first thing to look at here is, hold on just a second. All right, I don't know why my cursor is not showing up, but we'll just have to keep going. All right, so when you look at here, we talked about setup and hold time. So on the top section here, you can see the setup time is 3 nanoseconds. The hold time is 2 nanoseconds. Again, these TTL parts are fairly old, so they're not going to live up to our goal of hoping for a 0 nanosecond hold time. You can also see in the middle section here, essentially the propagation from low to high and high to low, which is our clock to Q, right? And you can see this runs, depending on the high to low or low to high, 25 to 40 nanoseconds. So slow compared to the numbers that we're used to. But again, these are discrete parts, right? And then finally, you can see here that the current that this requires, that ultimately goes to the power, is 25 milliamps. So this is the TI commercial grade Schottky version, the S version. If we look at the non-Schottky version, same kind of things, although realize now the setup time's 20 nanoseconds, the hold time's 5 nanoseconds, so it's a slower part. Right? But it's a little bit less power here down at the bottom at 15 milliamps. If we go to the LS, which is the low power Schottky version, similar kind of timing, similar kind of clock to Q and hold times, but notice that the power is significantly less. We're down to 8 milliamps versus where we were at 15 milliamps here on the non-LS version. All right. The last thing here on these parts is the fan out, which is how many gates a single part can drive. And remember, these TTL devices actually have an input current requirement. So if you look here at the top section of this table, it says the input current, IIL and IIH. The IIH is pretty small, 120 microamps, 40 microamps, right? Especially when you compare it to the IIL, which is the input current to pull the input low, right? That's in the 1.6 milliamp range for the D input. Also notice here that on the output current, how much output current these can provide, IOH and IOL. IOH is minus 1 milliamp. Well, that minus 1 milliamp has to match up with the 40 or the 120 microamps. And the IOL has to match with the 1.6 milliamps, and that's 20 milliamps. So in the picture down here at the bottom, you see if the max I can provide out for the low is 20 milliamps, but I need a minimum of 1.6 milliamps in, right? That says I can have a fan out of about 12-ish, right? So depending on which two things you're talking about, Any one gate can drive as many as, but not more than 12 other gates. All right, so now we're going to look at the SN74HC74 gate sheet, which is the CMOS version. All right, so here's the SN54HC and the SN74HC74. Again, a dual edge trigger D flip-flop, the same kind of part. Again, here's a simplified schematic. This is similar to the one that we drew with the pass gates and the latches and things like that. It's not drawn exactly the same way. And then there's a whole set of specs here. Here's the various pin-out configurations. So very much like the other one, a bunch of information about the specifications and things like that. Let's just pass down here and see if it's got some timing information just so that you have the right measurements. There's again the schematic. Here's some information on how to actually wire it up if you wanted to do that. Let's see what else is coming up here. Here's all the various packages just like before. And again, tape and reel are available, and then there's the box. Okay, so if we look at this SN74HC74 spec, right, we can see here that the clock high to low, or oh, did I lose it? Yeah, the clock high to low looks like it's in the range at 2 volts of 80 nanoseconds. So this is much slower than what we were talking about before. Before, the worst case was about 20 nanoseconds. Here we're at 80 nanoseconds. So these parts are slower, right? So here's the setup time. Again, before at the voltages we were talking about, they were in the 10-ish kind of nanoseconds for 10 to 20 nanoseconds for setup time. You can see here at 2 volts, this is 100 nanosecond setup time. But it does have, on the bottom here, our 0 nanosecond hold time, right? Which is a big deal when we try to build this system up, right? The real key here, what is this? This is the propagation delay. Again, this is clock to Q, anywhere from, looks like 70 to 200 nanoseconds. So again, one thing to note here is at the top it says with a CL equal to 50 picofarads. So this means, like we talked last time, with all the other things that are hanging off the output, maybe it's wires, maybe it's other gates or whatever, this is tested with all those things adding together to be 50 picofarads. So they guarantee these timings with that much stuff out there. You may have less stuff, you may have more stuff. If you have more stuff, then you've got a problem. If you have less stuff, then it'll operate a little bit quicker, right? Notice that the input current here at the top is in the nanoamp range, so it becomes essentially a who cares, and the input of one of these can be as much as, the input capacitance can be as much as 10 picofarads, right? So we said before these were tested at 50 picofarads with these timing, so if each gate has a 10 picofarad input capacitance, that means the most number of gates you can run would be 5. So I could have one gate fan out or drive 5 other gates if there were no wiring capacitance. If I had wiring capacitance, maybe I can only drive 4 gates or 3 gates, right? And so if I want to drive more than that, either I have to live with the parts slowing down, or I have to figure some way to make to spread out the gates so that we don't end up with an issue with them, right? Somewhere here I missed it, I guess. I wanted to look at the power. So let's see if I can find that real quick. Maybe it's still coming up, I don't see it yet. Let's look at connecting these things, right? So when we want to connect a TTL part to a CMOS part, on the top here is the TTL spec for the output levels, the output voltage levels. On the bottom is the CMOS part's input voltage requirements. You'll notice, and we'll look at the green one first, the one on the right, the output voltage for a low on the TTL part is 0.4 volts, and the input requirement to see a low on the CMOS part is 1.35 volts. So the TTL part pulls down more than far enough for the 1.3 for the CMOS part, right? But unfortunately, the TTL part only pulls up guaranteed to 2.4 volts for a high value. But the CMOS part on the bottom requires at least 3.15 volts to be measured as high. So we can't actually tie this TTL part directly to this CMOS part as it sits. We'd have to find what we call a level shifter, or a little piece of circuitry that would make these match up on the red path here. The other direction is fine. If we have a CMOS part driving a TTL part, and again, the top is the TTL, the bottom is the CMOS guarantees that it will pull up to at least 3.84 volts for a high output, and the TTL part only needs 2 volts to see a high input, so that's okay. And the CMOS part pulls down to at least 0.33 volts for a low output, and the TTL part only needs 0.8 volts to see a low. So we can drive CMOS to TTL. We have to add something if we want to drive TTL to CMOS. All right, and if we kind of look at the overall thing here, we can see the bipolar and the CMOS and the enhanced CMOS parts. Propagation delays, just looking at kind of maybe the LS column on the bipolar and the HC column on the CMOS. CMOS looks to be about half as fast. The VIHs are a little bit different. IOLs, IOHs. The big thing is down here towards the bottom, the IDD, how much current this part takes, right? And so for the LS bipolar, it takes 6.6 milliamps. For the HC CMOS, it takes 0.02 milliamps. This is why CMOS has taken over the world, right? It may be a little bit slower, but it's so much less power. Let's do that quick calculation. So you could do 50 CMOS parts for 1 milliamp. So that means you could do 300 CMOS parts for the same current as a single LS bipolar TTL part, right? That's the big deal. Now, because of that, the costs have changed. It used to be that the TTL parts were cheaper than the CMOS parts, but since CMOS has taken over the world, you get volume discounts, all the things that go with having huge production. The CMOS parts are actually even cheaper than the TTL parts today also. So again, power is the king, and the king is CMOS. All right, so let's talk a little bit more about power. There's two major power components, static power and dynamic power. Static power is the power when your part's just sitting there. Nothing's happening, no switching, nothing's going on, right? And so that power is the voltage that's applied to the part times what we call the static current, all right? The dynamic power is the current used to switch from 1 to 0 and 0 to 1, right? And so what you'll learn, if you haven't already learned it in your circuits class, is that the current is equal to the capacitance times the change in voltage over change in time. And we can estimate the change in voltage over the change in time to be VCC over the period, right? It's going to change from a 0 to 1 or a 1 to 0 once every period based on being clock driven, right? So we become C times VCC over 2, and then or VCC over T, and 1 over T is frequency, so we can say it's C times VCC times the frequency that we're running this part at, right? Well, power is current times voltage, so we get voltage times C times VCC times F, or we get capacitance times voltage squared times frequency. So that's the dynamic power, right? But note that since half the time we're pulling up and half the time we're pulling down, and we only consider the power when we're pulling up, right? Our power is 1/2 the capacitance times the voltage squared times the frequency. So you can look at this one equation and see why the voltages for parts have been dropping very quickly over time. Used to be 10 volts and then 5 volts and then 3.3 volts and 2.5 volts and 1.8 volts. And now a lot of circuits run at below 1 volt. And that's because you get a squared factor in the power, and power is king, remember. Right? So I can, for the same power, I can reduce the voltage and increase the frequency, or I can reduce the voltage and reduce the power. So that's why voltage has become such a big deal. Right? Now we're just going to look at some parts. Here's just a dual D-type positive edge triggered flip-flop with preset preset and clear. Nothing special there. We've seen that before. Here's this 8-bit serial in, parallel out shift register. So it's got a serial input, it's got 8 outputs, and you can just shift the serial value across it. Here's the opposite. It's a parallel in, serial out shift register. So it takes 8 bits in and shifts out one at a time through the outputs. Here's a bidirectional shift register, so 4 in, 4 out, right? And it can go either direction. Here's a parallel in, parallel out shift register, so it shifts them all in or shifts them all out together as a shift register. Here's an up-down counter. So this is a little bit different looking than our counter. It's got a little more logic associated with it, and that's because it's got 2 versions. It's got a binary coded decimal version, and that's the version that I think we're looking at here, right? So you can see it's got 4 flip-flops because it's a 4-bit counter, and a bunch of circuitry to decide what to happen with presets and clear and things like that. Now notice this has a preset. So a lot of this circuitry is associated with being able to force it to not start at 0, to start it anywhere you want to. I want to start at 5, I want to start at 9, I want to start at 13. I can set it to start at 13 and then start counting up or down, right? And then here's the binary version. You have to look real closely here. The logic, I'll flip back and forth between these two. It's the logic at the bottom that changes because we're moving from BCD here to just a regular binary counter there. What do we got here? This is a asynchronous first in, first out memory. So this is what we call a FIFO. And a FIFO says, all right, put a value into it, right? When you read it, you get the very first value you put into it. So if I were to put A and then B and then C into this FIFO, when I read it out, I would get A and then B and then C. First in, first out. There are what are called LIFOs, last in, first out. So if I were to put an A in and then a B in and then a C in to this, and it was a LIFO, I would get the C out first and then the B out and the A out. Right? It's much like the stack, if you remember from CE1911. All right, that's it for today. Enjoy your weekend.